Hi, this is Dan Fleisch. Julia's at the eye doctor today, but this is the podcast for Section 3 of Chapter 4 of A Student's Guide to the Mathematics of Astronomy. In this podcast, I'll be talking about angular resolution, which is a concept we are fully aware that many astronomy books don't go into too much detail about. Sometimes they present the equation by which you can calculate angular resolution, and you'll certainly find that at the end of this section. But one of the important parts of learning to think like a scientist is to understand where things come from. And in this case, we went to some detail to describe where the angular resolution equation comes from. So what is angular resolution? It's another important use of angles in astronomy, and if you look on page 111 at the beginning of the section called Angular Resolution Concept, you'll see the definition right there. It's the minimum angle over which two light sources, 2 point sources, can be seen as separate rather than blended together. So better angular resolution means smaller angular resolution. It means those two sources can be closer in angle and you can still resolve them as separate. That means your vision will be clearer when you have smaller or better angular resolution. To understand where angular resolution comes from, you have to think a little bit about waves and how waves add together. You can see a little bit about that on page 112 in figure 4.8. In this figure, we've shown in the upper left a couple of waves that arrive at the same place at the same time, and notice these two waves are in step. That is, this one is reaching a peak at the same place and time that this one is reaching a peak. They are lined up. That's referred to as being in phase. Likewise, when this one reaches its valley, this one reaches its valley. When two waves of the same frequency arrive at the same place at the same time, and they are in step or in phase, they add to give a bigger wave. That's what we're trying to draw here. They're adding, as we call it, constructively. So in everyday life, the word interference usually has a negative connotation. But when you're dealing with waves, interference can be constructive, as it is here, or it could be destructive. How does that work? Look out on the upper right. Here this wave is reaching its peak when this one is in the depths of its valley. These waves are out of step or out of phase. Likewise, this one's in a valley when this one's at a peak. When you add these two waves together, again, if they're the same frequency, arriving at the same place at the same time, and if they're the exact same size, they add completely destructively. That is, they produce a zero resultant wave. If they're not the same size, they produce a smaller wave than the larger of the two. But if they're equal in size, as I said, then you get zero wave out. You may be thinking, okay, but most of the time aren't they sort of in between, in phase and out of phase? That case is shown here. These waves are slightly out of phase, and that means they're offset not by 0 degrees, which is constructive interference, or 180 degrees, which is destructive interference. There's something in between. What do they add to? Well, if they're closer to being in phase than out of phase, they produce a larger wave than either of the two. But if they're closer to being out of phase, then they produce a smaller wave. Okay, so waves can add constructively, destructively, or something in between. What does that have to do with telescope lenses and mirrors? We're going to show the case of lenses here, and in pictures like figure 4.8, we're taking a slice through that lens so you can see what's happening from a side view. Now in this picture, there are light waves all coming from a point source. These are all light waves coming from the same point source, which is way out here somewhere. As a matter of fact, it's so far away that these light waves are coming in parallel to each other. Now you might say, wait, if it's a point source, they must be spreading out, because from a point, don't light waves spread out as they go? Why are these parallel to each other? The answer is we are so very, very far away, which we are for most objects in astronomy, that you can treat these lines of propagation of the light waves, as being parallel to one another. They strike a telescope lens, and again, you could use a mirror for this. I think it's a little easier to understand what's going on with a lens. The lens is shaped just right to make the rays converge, that is, come together in step at a place called the focal point. Later on, we'll talk about the whole area around which this happens called the focal plane. But for now, you've got a point source that is on the axis. The axis of the lens is the line through the middle of the lens, perpendicular to the lens. And if the point source is on the axis, the focal point is on the axis as well. So here's where the light waves come together. And we said the lens is shaped just right. We call that shape an ogive, and that guarantees that the waves are in phase at the focal point. So they add constructively right there. You may say, oh, so if they're adding constructively only at that point, then a true point source out here must produce a point on the focal plane here. Well, not quite. To see that, look at the next figure, 4.9 on page 113. Here, we've scooted things to the left a little bit so we could put a graph. This is a graph we've put on there so you can see what's going on the focal plane. And it's a graph of the brightness. It's on its side so that you can imagine moving up the focal plane, up here, and plotting the brightness of the light at every point. So here's the point of maximum brightness. That's where all the waves are adding in phase. But look at what happens if I keep going up away from that point, or down away from that point in the focal plane. The light doesn't fall off to zero instantaneously. It works its way down to zero on both sides, and there's finite width to that. We call that the PSF, which stands for point spread function, because it tells you how the brightness from a true point source is spread out slightly over the focal plane. It's not all at one point. Why does that happen, and how big is that thing? You can get an idea of that by looking at figure 410 on page 114. Why it happens is shown in the little text boxes here. Right at the peak of the brightness, the peak of the point spread function, all the waves are in step from the middle of the lens and the edges of the lens, and everywhere in between they're all in phase. As you move away on the focal plane, some of the waves, particularly the edge waves, begin to get out of step with the center waves, and so they don't add quite as constructively as they did at the true focal point. As you go farther away, you get to a point where the edge waves are completely out of phase with the center waves, and there they cancel. There's a zero brightness, what we call a null of brightness. And if you keep going away on the focal plane, you actually reach another point, these little so-called side lobes, where some of the waves are in phase, some of them are out of phase. This happens on both sides of the focal point. So the point spread function is really quite a complex looking little thing. Its actual shape depends on the shape of your lens, but the important point to understand is that the light is spread out over a finite area on the focal plane. Remember, we've only been dealing with a slice through the lens. We haven't been dealing with the entire lens. To see what that looks like, we've got to rotate this point spread function, and that's what's done here. Imagine taking this point spread function with its major peak and smaller side lobe peaks and all these nulls and rotating it, because the lens is a three-dimensional object, so this slice we took through it has to be rotated around to produce the brightness function in 3D. And here that is. This is meant to represent a three-dimensional plot where higher means brighter, so here's the peak of the brightness, and you see the side lobes around it this way. That's what a graph of brightness looks like, but if you actually turn it into an image, you get this thing down here. And if you've ever looked through a telescope, you might have seen something like this. This is the point spread function as it looks in an image. The bright central peak here, that's just the peak of the point spread function. And if you move away from it, it gets a little dimmer, and you get to a point where there's actually a dark line. Those are these nulls rotated around into different places on the focal plane. So you get these dark concentric circles around the bright central peak. That's sometimes called the airy pattern or airy disk that a point source produces on the focal plane of an optical instrument. The thing to take away is that that point source does not produce a true infinitesimally small point on the focal plane. It produces a region of brightness on the focal plane. Okay, what does this have to do with angular resolution? To understand that, you have to think about a second source, or it might be a second point on the same source, but imagine that it is slightly above the axis of the lens, so it's up here. its rays are coming in at a slight angle. All the angles in these graphs are grossly exaggerated to make it more clear. You say, wait a minute, you said they were so far away they should be parallel coming in. Yes, they are. They're still parallel, but they're angled a little bit downward because the source point is a little above where the original source point was. So what does that mean? When the rays converge, the lens still does its job. It still brings them to a point, but that point is slightly below the lens axis. This is the reason that lenses produce inverted images. If the source is above the lens axis, the peak of the point spread function is below the lens axis. It works left-right too, but again, we're taking a vertical slice through our lens. Notice that we still have the same point spread function. The peak is the same. It's just below the axis of the lens because the source was above the axis of the lens. So what happens if you have two sources, or 2 points on the same source? I couldn't draw the waves on here because it just got too confusing, so I just do these rays. Here are the ones that are coming in from one source, that is the one above the axis. Here are the ones coming in from the source on the lens axis. And just as before, each produces a point spread function, one on the axis, one below the axis. Here are those 2 point spread functions. Now, if you look at these right side up, you start to see something interesting. The 2 point spread functions, if the sources are close enough in angle, the 2 point spread functions can overlap. And when they overlap, some of the minor peaks of this one may fall over the major peak of the next one. If they're far apart, then each one would be well down into the very low brightness by the time you get to the other peak. But if they're close together, this region of overlap can start to blur the two together. Here we have two sources where I've deliberately positioned the first null of one at the first null of the other, and you can just barely see on this image. There's a little line through here that is the null between them. These two sources are resolved. That is, you can tell that there are two sources because there's a nice deep dip between them. In astronomy, we don't quite insist on the sources being that far apart in angle. We tend to use something called the Rayleigh criterion. The Rayleigh criterion says this: if two light sources are separated in angle by enough such that the peak of one and the peak of the other are not so close that either peak falls within the first null of the other, that is, if this second peak is outside the first null of this first peak, then they are said to be resolved according to the Rayleigh criterion. So that means there can be considerable overlap. Here are two sources clearly resolved well beyond the Rayleigh criterion, but here are two right at the Rayleigh criterion. Notice there's not a dark line through the middle. There's just a dip in brightness as you go between them. That's meeting the Rayleigh criterion for resolution. Okay, we're almost up to angular resolution equation. The other thing we have to consider, though, is what is the effect of the lens itself? That is, what does this resolution depend on? Well, in this figure, figure 4.17 on page 118, you can see what happens if you've got a large telescope lens and a small telescope lens. Again, you can substitute the word mirror here. It would work the same way, just with reflections instead of transmissions. Notice the large lens. The edges are far from the center, so these edge rays are coming in at a pretty steep angle. Once again, these angles are grossly exaggerated. And what does that mean? It means since the edges are farther from the center, as you move along the focal plane, you don't have to go very far before these edge rays get out of phase with the center rays. That means the point spread function is skinny. So large aperture, that is large lenses, produce thin point spread functions on the focal plane. Likewise, if you've got a very small lens, the edges are close to the center, and those edge rays, you have to go a long way on the focal plane to get them to come out of phase with the center rays. That means the point spread function is wider for a smaller aperture. And if the point spread function is wider, you can't have another source as close as you could in this case, that is the large aperture case, and still tell them apart. So what we're seeing here is that the width of the point spread function is inversely proportional to the aperture size, and that means the angular resolution is inversely proportional to the aperture size. As you might also have guessed, it also depends on the wavelength, because how far I have to move along the focal plane in order for an edge ray and a center ray to come out of phase depends also on the wavelength. If I have very long waves, I have to go a long way before that little phase difference adds up to something significant. So it turns out that angular resolution is directly proportional to wavelength. Those are summarized right here in 4.9 and 4.10 in the text. In 4.9, we show the proportionality relationship. Angular resolution goes inversely with aperture. Bigger aperture means smaller angular resolution, and smaller angular resolution is better. Likewise, equation 4.10 says wavelength, remember this lambda means wavelength, is directly proportional to angular resolution, so bigger wavelength means worse or bigger angular resolution. You can put those two proportionality relations together. We did that in the section called Calculating Angular Resolution, and proportionality relation 4.11 shows you that result. Angular resolution is proportional to wavelength in the numerator and inversely proportional to aperture. That's in the denominator. Remember, is proportional to means equals a constant times, and you can see that constant in equation 4.13. Depends on a couple things. Depends on the units you use. Depends on the shape of your aperture, the lens or mirror you're using. But for a circular aperture, if you want the angular resolution in radians, the constant comes out to be 1.22. If you use that constant, and whatever units you use for wavelength and aperture are the same, that is, they can be any units of length as long as they're the same units in the numerator and denominator, you will get the angular resolution in radians. So equation 4.13 is one way for you to calculate angular resolution. On that same page, you'll find an example. If you have a telescope with a diameter of 10 inches, that could be the diameter of the lens or mirror, and you use an invisible light with an average wavelength of about 550 nanometers, what resolution do you get? Plug those numbers in here, make sure you put them in the same units, multiply by 1.22, and you get a very small number of radians, which if you turn it into arc seconds, turns into something like half an arc second. That's an incredibly good resolution. You can see remarkable things with half an arc second resolution, but don't expect to get that performance out of your telescope because it turns out other factors limit this. Those factors include imperfections in the optical system and perhaps more importantly, the atmosphere we have to look through. Here in Ohio, we're very lucky if we get 2 or 3 arc second seeing, as we call it. That means the atmosphere limits us to many times bigger resolution, that is worse resolution, than the theoretical resolution of half an arc second for a 10-inch mirror or lens. As I mentioned at the start, most astronomy books have an equation for angular resolution, and it's probably not in radians. They probably give it in arc seconds. If you do this in arc seconds, the constant turns out to be about 0.25, assuming you use micrometers. That is not meters. For wavelength, you have to use micrometers. Remember, 1 micrometer is 10 to the minus 6th meters. So if you've got your wavelength in nanometers or meters, you have to convert it to micrometers before you use this equation. Happily, the aperture can be inserted in meters, and when you do that, multiply by 0.25, the angular resolution comes out in arc seconds. Okay, summarizing the main points for this section. Angular resolution is defined as the minimum angle that 2 point sources can be separated by for you to be able to see them as separate. And the description of the brightness of light over the focal plane is called the point spread function. Remember that angular resolution has 2 proportionalities. It is inversely proportional to aperture, so bigger aperture, smaller, that is better angular resolution. Longer wavelength means bigger or worse angular resolution for the same aperture. The 2 equations are given here. 413 gives you an answer in radians, 414 in arc seconds, and always remember that the achievable angular resolution is usually limited by factors other than the aperture of your instrument. Okay, that's it for this section. Julia will be back for the next. See you then.